August 1st, 2007, 6:05 p.m. 140,000 vehicles crossed the I-35 West Bridge in Minneapolis that day, just like they did every single day. Minnesota's third busiest bridge. Rush hour traffic, bumper to bumper. And then, it wasn't there anymore. 13 seconds. That's how long it took for 1,000 feet of steel and concrete to fall 108 feet into the Mississippi River. 13 people died. 145 were injured. And here's the thing that's going to make you angry. We're going to talk about how AI could have prevented every single one of those deaths. But first, let me tell you about a school bus. It's Wednesday evening. A group of kids from the White House Neighborhood Center are coming back from a field trip to a water park. 63 children on a school bus, stuck in traffic on the I-35W bridge. The bus driver is Kim Dahl. The kids are hot, tired, probably a little cranky after a long day. Traffic is barely moving because 4 of the 8 lanes are closed for construction work. There's 287 tons of construction equipment sitting on the bridge deck. Sand, gravel, concrete mixers, all staged for a concrete pour scheduled to start at 7 p.m. Nobody knows it yet, but that equipment is sitting directly over the bridge's weakest point. Now I want you to imagine you're driving on this bridge. You're in your car, windows down, maybe listening to music. It's a beautiful summer evening in Minneapolis. And then you hear it. A sound like a gunshot. A beam snapping. Then a loud metallic clank, and the bridge starts to shake. Kelly Kale was driving northbound in her car. She was heading to a soccer game. Normal Wednesday. And suddenly, and I'm quoting her directly here, she said it seemed like the north end of the bridge was rising into the air. But it wasn't rising. Her section was falling. She remembered screaming, "God, please don't let me drown. I don't want to die that way." Then muddy water with bits of concrete hit her window. And then suddenly, stillness. Her car was floating in the Mississippi River. Lindsay Walls was driving southbound. She described being in La La Land, thinking about the days ahead. Then the world exploded. Her car dropped 5 stories. When she came to, she had 3 compressed vertebrae, and her life had just been split into before and after, but back to that school bus. 63 kids. The bridge is collapsing beneath them in sections. Drivers around them are falling. Some cars plunge straight into the river. Others end up perched on twisted steel at crazy angles. The bus ends up resting against the guardrail of the collapsed section, precariously balanced. One wrong move, and it goes into the water with all those kids inside. Jeremy Hernandez was a 20-year-old staff member on that bus. And while chaos is erupting all around him, while people are screaming, while the bridge is still settling with these horrible metal-on-metal sounds, Jeremy does something remarkable. He kicks out the rear emergency exit, and then he starts getting kids out, one by one, escorting them, carrying them, getting them to safety. All 63 kids survived, but not everyone was that lucky. 11 vehicles were on the portion of the bridge that collapsed. 17 of them ended up in the river. The Minneapolis Fire Department arrived in 6 minutes. 6 minutes. That's incredibly fast. They had 81 minutes to triage and transport 145 patients. First responders worked through the night. The last victim wasn't recovered until August 20th, 19 days later. 13 people didn't make it home that night. And here's what's going to haunt you. This bridge had been rated structurally deficient since 1990. 17 years of inspections noting problems. Cracking, corrosion, fatigue. In 2001, 6 years before the collapse, a University of Minnesota study specifically recommended structural health monitoring and the use of strain gauges for this bridge. In 2006, just 1 year before, they actually planned to reinforce the bridge. They were going to do it. But then engineers realized that drilling into the structure to install the reinforcements would actually weaken it further. So they canceled the project and went with periodic safety inspections instead. In 1999, 8 years before 13 people died, inspection photos showed that critical gusset plates were bowing, bending, visible deformation. Those photos existed. They were in the files. The bridge knew it was dying. It was screaming for help in ways that human eyes during a visual inspection couldn't see, or didn't know how to interpret. But you know what could have seen it? Sensors, strain gauges, AI analysis. The technology that could have saved those 13 lives existed in 2007. It exists today, and I'm going to show you exactly how it works. But first, we need to understand what actually killed this bridge. Because it wasn't age. It wasn't deferred maintenance. It wasn't even the construction equipment, though that was the final straw. It was a design flaw that existed from day one. A mistake made in 1961 that nobody caught for 46 years. A calculation error that involved something called a gusset plate, and it was half an inch too thin. Okay, so a bridge doesn't just fall down. Especially not a major interstate bridge that's been standing for 40 years. Something has to fail. And when the National Transportation Safety Board started investigating, they found something that made every bridge engineer in America go back and check their own designs. Let me introduce you to the villain of our story, the gusset plate. Now, if you're not a structural engineer, you've probably never heard of a gusset plate. But they are everywhere in steel truss bridges. Think of them as the connectors. Flat steel plates that join multiple truss members together at what we call nodes. The I-35W bridge was a steel deck truss design. Beautiful, efficient, elegant engineering. The main truss had these diagonal members, vertical members, and horizontal cords all working together to distribute load. And at every connection point, every node, you had these gusset plates bolted or riveted to hold everything together. These plates have to handle tremendous forces. Tension pulling in one direction, compression pushing in another, shear forces trying to slide things apart. It's a complex stress state. And the thickness of these plates? Critical. Absolutely critical. So the NTSB starts investigating. They're looking at everything. Corrosion? Yes, there was some. Cracking? They found some of that too. The weight of all that construction equipment? Definitely a factor. But then they zero in on node U10. Node U10 was where the diagonal and vertical members met the upper cord on the main truss. And when they examined the gusset plates at node U10 after the collapse, they found something that made their blood run cold. The plates were half an inch thick. They should have been 1 inch thick. Let me put that in perspective. These gusset plates were designed by an engineering firm called Sverdrup and Parcel back in 1961. Somebody, we'll never know exactly who, because the lead designer has since died, made a calculation error. They specified gusset plates that were only half as thick as they needed to be. Not at every connection point, just at specific nodes. The bridge had 16 under-designed gusset plates that were too thin. The rest were fine, properly designed, stayed intact during the collapse. But those 16 plates? They were ticking time bombs. And here's what makes this even more frustrating. This wasn't a new problem that developed over time. This was baked into the design from day one in 1961. The bridge was built wrong. It opened to traffic in 1967, already carrying a fatal flaw. The NTSB's official finding? The probable cause of the collapse was the inadequate load capacity due to a design error of the gusset plate at the U10 nodes. But wait, it gets worse. Remember I mentioned those 1999 inspection photos? Let me tell you about those. In 1999, 8 years before the collapse, routine inspection photos showed that the gusset plates at node U10 were bowing. They were visibly deformed, bent. You could see it in the photographs. Now, to be fair to the inspectors, they didn't necessarily know what they were looking at. Structurally deficient doesn't mean unsafe in bridge inspection terminology. It means the bridge doesn't meet current standards, but is still considered safe for traffic if properly monitored. But those bowed plates? That was the structure screaming at us. That was metal under stress, deforming, begging someone to notice that something was wrong. And it wasn't just the undersized gusset plates. That was the original sin. But then we added insult to injury, literally. Over the years, the bridge deck had been resurfaced multiple times. Each time they added another layer of asphalt and concrete. By 2007, there were 2 inches of concrete that hadn't been there originally. 2 inches doesn't sound like much, right? But spread across the entire deck of a 1,900-foot bridge? That's a lot of weight. The NTSB calculated it increased the static load, the dead weight the bridge was carrying, by 20%. 20% more load on gusset plates that were already only half as thick as they should have been. And then, on August 1st, 2007, we added the final ingredient to this disaster recipe: 287 tons of construction equipment and materials. Sand, gravel, concrete mixers, paving equipment, all staged in the closed southbound lanes for that concrete pour, scheduled to start at 7 p.m. And where was all this equipment positioned? Right above node U10. It was like we took the weakest point on the entire bridge and said, hey, let's put the heaviest possible load directly on top of it during rush hour traffic. The construction foreman actually asked a Minnesota Department of Transportation inspector about setting up the equipment in the middle of the bridge. Got verbal approval. But according to testimony later, MNDOT said that should have been a formal written request, which would have been denied. Communication breakdown. Probably not malicious. Just people doing their jobs, not knowing they were creating the perfect conditions for catastrophe. At 6:05 p.m., with rush hour traffic crawling across the bridge, with 287 tons of equipment bearing down on node U10, with those half-inch gusset plates that should have been an inch thick already bowed and stressed beyond their design capacity, something gave way. The NTSB investigators, using recovered security camera footage from the Lower St. Anthony Falls lock and dam, were able to piece together the exact sequence of failure. It started with lateral instability at the upper end of one of the diagonal members connected to node U10. That caused the gusset plates at the U10 nodes to fail. They didn't just crack, they ripped along the line of rivets. Catastrophic failure. And here's the nightmare part. The I-35W bridge was what's called non-load path redundant. Engineering speak for, if one critical piece fails, the whole thing goes down. No backup system. No redundancy. One point of failure. Once those gusset plates at node U10 failed, the total collapse of the deck truss was unavoidable. 13 seconds from first failure to complete collapse. Now, the NTSB looked at other potential causes. Could corrosion have caused this? No, there was corrosion, but it didn't play a role in the collapse. Could pre-existing cracks have propagated? Nope, those weren't the problem either. Could temperature effects have contributed? Maybe slightly, but not the primary cause. The bridge bearings were partially frozen due to corrosion, which limited their effectiveness and might have introduced some additional expansion stresses. But again, not the primary cause. The primary cause was simple, brutal, and preventable. Design error. Undersized gusset plates. Quality control failure. Inadequate design review. You know what haunts me about this? In December 2006, they planned a steel reinforcement project for this bridge. They were going to fix it. Engineers identified problems and developed a plan. But then they realized that drilling into the structure to install the reinforcements would weaken the bridge further. So in January 2007, 7 months before the collapse, they canceled the project in favor of periodic safety inspections. Internal MNDOT documents from that time show bridge officials talking about the possibility of the bridge collapsing. They worried about having to condemn it. They knew. They didn't know when or how, but they knew this bridge was in trouble. After the collapse, the federal government gave the I-35W bridge a rating of structurally deficient, but so did 75,000 other bridges in America in 2007. The bridge scored a 50 out of 100 on the sufficiency rating. Only 4% of heavily used bridges scored below 50. So yeah, it was in the bottom tier, but not so bad that anyone thought it would actually fall down. The inspection carried out on June 15, 2006, just over a year before the collapse, found problems of cracking and fatigue. But the bridge was deemed to have met minimum tolerable limits to be left in place as is. Minimum tolerable limits. Those are the words we use right before something catastrophic happens. So here's what we know. A design error in 1961 created gusset plates that were half as thick as they should have been. Photos from 1999 showed those plates were bowing under stress. Multiple inspection reports noted problems. Engineers were worried enough to plan reinforcements, then too worried to actually do them because the cure might kill the patient. And through all of this, 17 years of knowing the bridge was structurally deficient, 8 years of having photographic evidence of plate deformation, 7 months of internal discussions about potential collapse, nobody had real-time data on what was actually happening inside that structure. No sensors measuring strain, no continuous monitoring of stress levels, no AI analyzing patterns, no early warning system, just periodic visual inspections by human beings trying their best with the tools they had. And you know what? I don't blame the inspectors. They were doing their job. I don't even really blame the engineers who canceled the reinforcement project. They were genuinely worried about making things worse. The real tragedy is that we had the technology to monitor this bridge in real time. We just didn't use it. So let me show you what should have been on that bridge. Let me show you what is on the replacement bridge today. Let me show you why 42,000 structurally deficient bridges in America right now need this technology. Because if we can prevent just one more I-35W, isn't it worth it? August 1st, 2007. The I-35W bridge collapses at 6:05 p.m. September 18th, 2008. The new I-35W St. Anthony Falls Bridge opens to traffic at 5:00 a.m. 13 months. They built a brand new bridge over the Mississippi River in 13 months. Normally that takes 3 to 5 years. But this wasn't normal. This was Minnesota saying, never again. And here's what makes the new bridge different. 323 sensors. 323 sensors constantly measuring bridge conditions. Deck movement, stress, temperature, strain. All feeding data in real time to computers at the University of Minnesota. The old bridge had 0 sensors, 0 continuous monitoring, just visual inspections every year or two. The new bridge? It's talking to us, constantly, telling us exactly how it's feeling, what it's experiencing, where stress is building. This is what I-35W should have had all along. So let's talk about how modern structural health monitoring actually works. Because this isn't science fiction. This is happening right now on bridges around the world. First, you've got sensors. Lots of different types depending on what you're measuring. Strain gauges that detect deformation in structural members. Accelerometers that measure vibrations. Tilt meters that track any shifting or settling. Temperature sensors, because thermal expansion is a real thing that affects bridges. Fiber optic sensors that can measure strain across long distances. These sensors are tiny. They're wireless. They're incredibly power efficient. Some of them run for 10 years on a single battery. And they're cheap. We're talking hundreds of dollars per sensor, not thousands. To install them at critical points on the bridge, places where stress concentrates, connection points, mid-spans, anywhere you want to know what's happening inside the structure. And then the magic happens. All that sensor data flows into AI algorithms that are trained to recognize patterns. Normal patterns versus abnormal patterns. Healthy bridge behavior versus stressed bridge behavior. Remember those gusset plates that were bowing at node U10 back in 1999? With strain gauges at that location, AI would have detected the deformation immediately. Not in 8 years. Not in 8 months. In real time. AI can process massive amounts of sensor data and predict potential structural failures with over 90% accuracy. Think about that. 90% accuracy in predicting failure before it happens. How? Because AI learns what normal looks like for that specific bridge under different conditions. Traffic loads, temperature changes, wind, seasonal variations. It builds a baseline. And then when something deviates from that baseline, when stress patterns start to change in ways that indicate damage or deterioration, the system flags it. Early warning. Days, weeks, sometimes months before catastrophic failure. Let me give you a concrete example. Those half-inch gusset plates at node U10 were failing slowly over time. The bowing visible in 1999 photos wasn't something that happened overnight. Metal doesn't just suddenly deform. It was stress building up gradually, the plates yielding under load, microscopic changes accumulating. Strain gauges would have caught that. They measure deformation at the micro level. AI analyzing that data would have seen the trend. Hey, this gusset plate is deforming more than it should. The rate of deformation is increasing. This is not normal behavior. Alert sent to engineers. Engineers investigate. They discover the undersized plates. They implement traffic restrictions while they develop a repair plan. They close the bridge if necessary. Nobody dies. Nobody gets injured. It's an inconvenience, sure, but it's not a tragedy. Now I know what you're thinking. Brian, sensors and AI sound expensive. We've got 42,000 structurally deficient bridges. We can't afford to monitor all of them. Actually, we can't afford not to. Here's the math. The old I-35W bridge collapse cost Minnesota an estimated $400,000 per day in lost economic activity. $17 million in 2007 alone. $43 million in 2008, plus the human cost. 13 lives, 145 injuries, decades of trauma for survivors and families. The replacement bridge? $234 million. Now compare that to the cost of a structural health monitoring system. We're talking maybe $100,000 to $500,000 to equip a major bridge with comprehensive sensor networks and AI monitoring. For smaller bridges, even less. One prevented collapse pays for monitoring systems on hundreds of bridges. And the technology keeps getting better and cheaper. Researchers have shown that just 2 mobile sensors mounted in vehicles that regularly cross a bridge, can provide structural health monitoring information comparable to 240 static sensors. Crowdsourced bridge monitoring. Your phone's accelerometer in your car provides data as you drive across a bridge. Multiply that by thousands of vehicles per day. Feed all that data into AI, and you've got real-time structural assessment for almost no cost. Studies suggest this approach could increase the lifespan of new bridge structures by 30%. 30%! By helping maintenance teams intervene faster and more precisely. The French government has actually launched a Connected Bridges initiative to support development of innovative, efficient, and economical solutions for bridge management. They get it. Other countries are implementing this technology rapidly. So why aren't we doing this everywhere in America? Good question. Part of it is inertia. We've been doing visual inspections for decades. That's what bridge inspectors know how to do. Changing an entire inspection paradigm across thousands of jurisdictions takes time. Part of it is funding. State and local transportation departments are stretched thin. The Federal Bridge Formula Program from the 2021 Infrastructure Law is helping. $27.5 billion for bridge projects. But that has to cover repairs, replacements, and upgrades for over 600,000 bridges. And part of it is just awareness. A lot of transportation officials don't know this technology exists or how effective it is. They're still thinking about bridges the way we did in 1967 when I-35W was built. But here's the thing, we can't wait, because those 42,000 structurally deficient bridges, they're not getting younger. They're aging, deteriorating, and 168 million trips are taken across them every single day. Let me tell you about some bridges that are using this technology. The Golden Gate Bridge has an extensive array of accelerometers, strain gauges, and displacement sensors, monitoring dynamic responses and structural health. The Akashi Kaikyo Bridge in Japan uses accelerometers to monitor oscillations caused by typhoons and traffic loads. The Forth Road Bridge in Scotland incorporates fiber optic sensors to detect strain and temperature variations over long spans. South Korea's Smart Bridge project employs wireless sensor networks and AI algorithms to assess structural integrity in real time. And right here in America, the new I-35W bridge in Minneapolis. There are 23 sensors, continuous monitoring, data analysis by University of Minnesota engineers. It works. The technology is proven. We just need to deploy it. Now I want to be clear about something. AI structural health monitoring doesn't replace human engineers. It empowers them. You still need bridge inspectors doing visual assessments. You still need engineers analyzing the data and making decisions. AI doesn't make the final call on whether to close a bridge or implement traffic restrictions. What AI does is give engineers information they've never had before. real-time visibility into what's happening inside the structure, early warnings of developing problems, predictive analytics that help prioritize maintenance and repairs. It's like going from checking your health once a year at a doctor's visit to wearing a smartwatch that monitors your heart rate, activity, sleep, everything continuously. You still go to the doctor, but now the doctor has way better data to work with. And here's the beautiful thing about AI and structural monitoring. It gets smarter over time. Every bridge it monitors adds to the knowledge base. Every failure mode it detects, every pattern it learns, every correlation it discovers between sensor readings and actual structural condition, all of that improves the algorithms. Digital twins are the next frontier. You create a digital replica of a physical bridge, feed it real-time sensor data, run simulations of different load scenarios, and predict how the structure will behave under various conditions. Shell uses digital twins for deepwater oil platforms. They run simulations and test different configurations to ensure infrastructure is optimized for safety and efficiency before actual construction. Equinor uses digital twins of oil and gas facilities to enable operators to fully understand facility performance and maintenance in a risk-free setting. We should be doing this for every major bridge in America. Build the bridge. Build its digital twin. Monitor both. Let AI compare the real-world behavior to the predicted behavior and flag any discrepancies. So, where do we go from here? As of 2024, we had 42,167 bridges classified as structurally deficient in the United States. That number has been slowly declining. It was 42,391 in 2023. Progress is happening. States are making repairs. But at the current pace, it'll take 40 years to address all the bridges that need work. And that's just the ones we know about. That's not accounting for bridges that will deteriorate into poor condition over the next 40 years. We need a faster approach. And AI structural health monitoring is part of the answer. Equip every structurally deficient bridge with at least basic sensor networks. Prioritize the highest traffic bridges, the fracture-critical designs, the ones with known issues. Get AI systems monitoring them continuously. Use the data to make smarter decisions about where to allocate repair funding. Which bridges need immediate attention? Which ones can wait? Which ones just need traffic restrictions while we plan major work? And for new bridges, make structural health monitoring a standard feature. No more building blind. Build smart from day one. The replacement I-35W bridge cost $234 million and was completed in 13 months. 3 months ahead of schedule. On budget. 0 safety incidents during construction. That bridge has 323 sensors. It's equipped with anti-icing systems. It's built with high-strength concrete designed to last 100 years. It has multiple layers of redundancy. If one element fails, others carry the load. It's everything the old bridge wasn't. It's built to communicate its health status. Built to last. Built to be monitored. And you know what? The people of Minnesota drive across that bridge 140,000 times a day, and they feel safe. Because they know it's being watched. They know if something goes wrong, engineers will know about it immediately. That's what we need for every bridge in America. 17 years ago, the I-35W bridge fell into the Mississippi River because we didn't know what was happening inside that structure. We had warning signs, bowed gusset plates, structural deficiency ratings, engineering concerns, but we didn't have real-time data. We didn't have AI telling us this is about to fail. Today, we have that technology. It exists. It works. It's affordable. The question isn't whether we can prevent the next I-35W bridge collapse. We can. The question is whether we will. Because 168 million trips across structurally deficient bridges happen every single day in America. And somewhere out there, there's another bridge with bowed components, overstressed members, developing cracks that visual inspections aren't catching. We have the tools to find it before it falls. Let's use them. I'm Brian. Thank you for watching. What's your opinion on using AI for bridges? I genuinely would love to know. If this video has given you value or inspiration, consider giving it a thumbs up and maybe consider subscribing. No pressure. Until next time. Stay happy, be healthy, and I'll catch you on the next flight.